Welcome to Hartman Math. We're going to talk inverses today. Before we get to that, go ahead and work through warm-up problems 1, 2, and 3. Pause here. Resume when you're ready. All right, so number 1, we've got a few transformations to look at. We're going to, for part A, shift left 2. So that would essentially subtract 2 from all the x coordinates. So there's our graph there. A couple different things going on in part B. We're going to stretch vertically by a factor of 3, which multiplies the y coordinates by 3, and then shift down 1, which subtracts the y coordinates by 1. So we get these points here. And then for part C, we're going to vertically shrink by a factor of 1/2 and shift 2 to the right. For number 2, practicing a difference quotient problem, you should have gotten 2x plus h, where h cannot be 0. And then even, odd, or neither on these. We've got odd for f of x, even for g of x, neither for h of x. This is lesson 1.9, inverse functions, where we have a relation that maps from set A to set B. And our function is f of x equals x plus 4. So 1 plus 4 is 5, 2 plus 4 is 6, 3 plus 4 is 7, 4 plus 4 is 8. The inverse undoes that and brings us, if we input 5, brings us back to 1. So the inverse, kind of think almost in terms of opposite. A pretty simple example here would be subtracting 4, so which takes us from 5 back to 1, 6 back to 2, and so on. The notation that we use for inverse of f would be f, and it looks like an exponent of -1, but as f is not a variable and does not have value, it's a name, this is just notation. So f inverse is the way that we usually say that, or inverse of f. So we have the domain of f. We take a function and it maps it to the range, and then the inverse is going to take that. It's now the domain of the inverse, and it maps us back to the range, which is the domain of the original. So definition, and this is really critical, the definition of inverse functions, because later when we verify, we do so by the definition here, which is that if we have two functions and we compose them, and the answer, f of g of x, the answer is x, for every x that's in the domain of the inner function, and vice versa, if we switch it around and do g of f of x, and that's also x for every x that's in the domain of f, then in fact our two functions f and g are inverses. So if we do find f inverse and we're verifying it, we're going to show it like this. We're going to do these two compositions. When we get there, we're going to be very careful and state the title for each. So this and this. And it doesn't really matter which one we do first, but you do have to have the title, and we do need to get a result of x. But before we get to that, actually we are going to get to that, verify that which of these happens to be inverses. So we've got these three functions. So we need to compose them, and if we get an answer of x, then we know that they should be inverses. So if we try f of g of x first, which means we're going to take the g function and plug it in here. So 5 times this plus 8. And as you go through, you can only cancel one thing at a time because I'm going to be carefully checking the work. In this case, 5 divided by 5 cancels. X minus 8 plus 8. And then that becomes x. So those two are inverses. we could do the same with h, and we're going to see it just doesn't work out. So g is the inverse of f. If we're looking in terms of graphs, we've got our f of x that's graphed. The inverse must be the reflection of that function and its graph in the diagonal line y equals x. They have to be reflections if they are inverses. All right, we remember that there's a vertical line test to determine if a relation is a function. Well, there is a horizontal line test to determine if a function is a one-to-one function, or it's not one-to-one, or this book would say many-to-one. So we need it to be one-to-one in order for it to have an inverse. In order for our function to have an inverse, it has to be a one-to-one function. So now, define that. What does that mean? A function is one-to-one when each value of the dependent variable, that's the y-coordinate, corresponds to exactly one value of the x-coordinate. So we cannot have multiple x-coordinates have the same y-coordinate. So if we pass a horizontal line across, it cannot hit more than one point at any time on the graph of the function. And we need our function to be one-to-one in order to be able to get an inverse. So example number 5, is this function one-to-one? We could look at it in terms of a graph. We'd say, hey, that's a parent function, that's our squaring function, that's a parabola. And then check the the horizontal line test. If we look at it, this horizontal line here, or pretty much any horizontal line, it hits more than one point. So as you can see, f of 2 is the same thing as f of negative 2. And that cannot be true for a one-to-one function, so this is not one-to-one. Okay? We cannot have two different inputs give the same output. So it's not one-to-one. Or this book would say it's many-to-one. Either way is fine. All right, checkpoint. What about g of x? Is that one-to-one? Well, if we thought about the parent graph, x cubed, past the horizontal line test up and down, it's never going to hit more than once. It is one-to-one. So we could find this inverse. We cannot find this inverse without manipulating the domain so that it is one-to-one. So these are the steps for us to be able to find an inverse. First of all, decide if we can. If we can't, we might still proceed by cutting down and restricting the domain such that it would pass the horizontal line test and be one-to-one. As long as we can proceed, replace f of x with y, switch all the x's and y's, go ahead and solve for y, switch back to function notation by writing f inverse of x, and then if we need to, go ahead and do the composition to verify that they're inverses. Example number 6, find the inverse. Is it one-to-one? Let's see, we've got a cubic function that's stretched vertically and shifted down 1. Should still pass the horizontal line test. We should be good. It's one-to-one. We can now proceed. So kind of combine a couple steps here. Y equals, and then switch all the x's and y's. Now we solve for y. So let's add 1 to both sides. Let's divide by 2 on both sides. And then to undo the exponent, let's cube root both sides. And then we can change it back into inverse notation, function notation. F inverse of x is the cube root of x plus 1 over 2. Now let's see if we can verify that that is in fact the inverse of that by doing the composition both ways, making sure we get x as our answer. So it doesn't matter which one we start with, but you have to start with a title. Which one are you doing? Gotta have it, because if you just start plugging something in, I'm not going to know which one's which, so I can't give you credit for that. So we need to have the title. So we're going to plug this one into F. So this function gets plugged into F, and it replaces X. So 2 times this cubed minus 1. And now the algebra in this case dictates, and one canceling at a time. If you do more than one, violation. We're going to essentially cancel out cube root and cubing to get 2 times this minus 1. And now 2 divided by 2 cancels. We get x plus 1 minus 1. And that equals x. All right, let's do the other one. So we need the title. We're going to reverse it. We're now plugging f in to the inverse. So we've got a big old cube root. We got a fraction. X gets replaced with this, plus 1 over 2. Now above and below fraction bars, we would simplify here. The parentheses don't really do anything for us here. The minus 1, the plus 1 cancel out. 2 divided by 2 cancels out. Cube root of x to the third is x. We got that check. I will let you know what I'm usually checking for is not this, but the algebra. And I'm really checking the step before. Notice on this one we had cube root of x to the third. And the last one, we had x plus 1 minus 1. If your your step before for both of these look very, very similar, that's usually a bad sign that you've made an algebra mistake there. So watch out for that. I've got to verify. Example 6.5, exploring domain and range. We just came up with these inverses, so we're going to take a look at what we've got by just taking a look at some points, such as f of 0, if I plug in a 0, I get negative 1. Over here, if I plug in negative 1, f of negative 1, I would get 0. If I plug in a 2 over here, 2 cubed times 2 minus 1, I get 15. If I do f inverse of 15, 15 plus 1 is 16, divided by 2 is 8. Cube root of 8 is 2. If over here I plugged in A and got B, what do you think would be a point on the graph of this? It's going to be B comma A. Notice that x and y here got reversed and became y and x here. So we're just reversing the coordinates. We saw that at the very beginning of the lesson. So what that means for us in domain and range, since we're switching x's and y's in here, the domain here needs to match the range here, and vice versa. The domain here needs to match exactly the range over here. So let's take a look. Example 7, find the inverse. Okay, if we were to look, is it 1 to 1? We're talking about a square root. 2 being multiplied inside is actually a horizontal shrink, but it still passes. And then we're going to shift in some fashion here to the right, still is going to pass. So we're okay. It is 1 to 1. We're ready to go. So to find the inverse, we're going to say y equals, switch x and y. Go through that process, and you would get x squared plus 3 over 2. There's an extra condition there. Because the domain here, we would say 2x minus 3 has to be greater than or equal to 0. If we then solve that, we get the domain, bracket 3 halves comma infinity. the range, since we took our parent function, shrunk it horizontally, shifted to the right, the range never changes. It still starts at 0 and goes up, so that's our range. We go over to our inverse. The domain here, even though this as a function unto itself is just a parabola, negative infinity to positive infinity, can't have that be true for the inverse function because its domain has to exactly match the range over here. So the domain for this, which must be included, even if it's not asked for, is from 0 to infinity. And the range should match over here, like that. In terms of the graphs, here is f. Remember, we talked earlier that the inverses have to be reflections of each other in this line, y equals x. So if we had not restricted the domain here, we would have gotten a full parabola. But then they're not reflections of each other because this doesn't have the part below because we're just talking about square root. So that's why this is so critical. More example 7. Find the inverse if possible. So again, we've got a square root shifted up 1. So it does pass the horizontal line test. It is 1 to 1. So if we put y equals and switch the x and the y, subtract 1 both sides, square both sides, that, but again, we're going to have to talk about the domain and restrict that because what's the range here for the original function? That's going to have to be the domain over here. Again, we don't want the whole parabola. Since the range here was 1 to infinity, that has to be our domain for the inverse. This is our last thing, or checkpoint. Here's our f of x. Go ahead and find f of f inverse of root 2. Pause the video here to work through it. Return when you're ready. All right. This is pretty tricky. If you tried to find the inverse of this function, good luck. It would be nasty, super complicated. Luckily, we don't have to know what the inverse is, because according to the definition, a function and its inverse undo each other. So if this was x, we would get x. Since this is root 2, the answer is the square root of 2. Because they do cancel out, that is what inverses do. That's it for today. I'll see you next time.